Alright, hello everyone and welcome to my video on the periodic table. There will be 7 sections of this video, going through a lot of these notes that we've taken in class and just giving some examples. So our 7 sections, we're going to start with just the basic structure of the periodic table. Then we're going to move on to electron or metals and nonmetals. What are the differences, and just showing you that on the periodic table as well. We're then going to get into ionic electron configurations. This includes both regular ions and um, transition metal electron configurations. Then we're going to move on to the periodic table and the electron configuration, just going over how it's set up, all of that fun stuff. Then we are going to get into the noble gas electron configuration. Um, then we're going to get into valence electrons, and finally, for my honors chemistry class, we're going to get in some of the exceptions and just explaining why there are exceptions. So let's jump straight into section 1, the basic structure of the periodic table. I link the periodic table, ptable.com, wonderful resource. It's what I've used to print out everything in class. It's right here, but I'm actually going to open this up and bring us to ptable.com because it's so interactive. So the first thing that I just want to go through and just show us is the general structure of it. We start over here with hydrogen in the top left corner, and our atomic number here is 1. We move left to right from the top down in terms of atomic number. So element 1, 1 proton, hydrogen. Element 2, 2 protons, helium. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and so on. We get down here, 19, 20, 21, 22, etc. All increasing by 1 till we get to 36. When we get down here, things get a little wonky, and what I like about this website is that this shows us the full structure of the periodic table in order. Here are these elements. It shows us this in the order of the numbers, of the atomic numbers. You can see here, just there are no numbers at the top. There's no columns. We don't consider them parts of this groups. But just to show you the general, increasing by the atomic number, just how this would look. And this also does kind of help us when we get into electron configurations in a little bit. So let's get off of the wide mode. The first thing that we want to talk about is just groups and periods. And these are some of the just super important terms that I'm going to be using a lot. And you are going to have to just know these terms. I can't have you not knowing these terms. Please don't get them confused. There's a few things that you just absolutely need to know. This is probably one of them. These are the groups. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 18. 18 groups. They are the columns. These elements are in group 16. So when I say group 16, that's what I'm talking about. Group 2. Here's group 2. Group 5. Again, we're not going to consider these elements in groups. We're not even going to talk about them at all this class. We'll talk a little bit about them, but not their electronic structure, not anything like that. We'll talk about them in nuclear chemistry. So you need to know these groups, up and down, group 11, etc., and so on. Okay? The other thing that we need to get through is the periods. Here's period 1. There's 2 elements in there. 2 elements. Just hydrogen and just helium. Here is period number 2. And then 3, 4, 5, 6, and 7. And just to show you when we actually do have this in wide mode, the periods do make a little bit more sense and shows us 1, 2, 3, 4, 5, 6, 7, just how this is. So these elements, the lanthanoids, they do have a period, but they don't have a group. But we're not going to really talk about them. The next thing that I do like about this periodic table, ptable.com, is it actually highlights, for those of you that like color coding, it does highlight some of these groups. So if we go here, we can see the alkali metals. These are group 1s. So we're talking lithium, sodium, potassium, rubidium, cesium, and francium. Hydrogen is a gas, so it does not act as an alkali metal. It's kind of an outlier. But this is group 1. The alkaline earth metals are group 2, from beryllium down to radium. We have the noble gases over here in group 18, so helium down to radon, and then there's no label for it, but here is group 17 is the halogens. Those are just things that I want you to know for when I use those terms in this class. So you will need to know those terms, difference between alkali metals and alkaline earth metals. We also have the transition metals, which are the metals smack in the middle. Um, and we will talk about these in this class. We'll talk about some of their properties and how they're going to form bonds. We're going to be using them in this class as well. Um, so it is important just to notice when I talk about transition metals, this is what I am talking about. Speaking of metals, here are the metals. And as you can see, it is most of the elements. Most of the elements are metals. The vast majority of them are. These are the nonmetals. Not that many. We have hydrogen all the way on the left, and then all of the noble gases, and then a few, towards the right. These are the nonmetals. In the middle here are the metalloids. It's really 6 or 7 elements that are somewhere in between a metal and a nonmetal. Um, their properties, it depends on which property. Some are more brittle, some are more shiny, etc., etc. Just for the record, these elements down here, they last for so long, so short of a time that it's really impossible to get any properties about them. Their half-lives, they disintegrate basically in such a fractions of a second. Okay, so some of the differences between metals and non-metals is just metals are shiny. If we really want to just, they're shiny. They look shiny. Most of them are gray. Non-metals are dull. You think of a pencil. Pencil is very dull. Its tip is not shiny. That's carbon. That's a non-metal. Whereas metals, you think of, copper, gold. Those are shiny things. Metals are usually solid. There's a few exceptions, but they're usually solid, which means that they have a high melting point. Um, they're solid at a much higher temperature. Most of the nonmetals are, if they're not solids, they are liquids or gases, right? Noble gases. Oxygen is a gas. Nitrogen is a gas. Chlorine, they are gases. Whereas there's no gases as metals. Metals are good conductors because electrons can flow right through them based off of the bonding, which we'll get to in our next slide. And nonmetals are poor conductors. Trying to run electricity through carbon, not going to happen. Metals are usually more dense. This is mostly due to their bonding and because they're solids. You compare a solid to a gas, the solid's going to be more dense. Whereas nonmetals have a much lower density. Carbon is very, very light compared to, say, a big chunk of iron. And lastly, metals are malleable. If you take the best example of this is taking a paperclip. You can very easily bend that paperclip into an entire shape. You can mold it. You can't really do that with a nonmetal. You take something like a wood, it's going to snap. It takes a lot more force to snap a paperclip. And just finally, the bonding of metals, they have this sea of electron. So when you have all these are the metal atoms, so let's say you have a big chunk of iron or something like that, or you have some copper, you have a copper coin. It's going to look like this, where the electrons can move all the way around pretty easily. They're not really shared. They're not tied down to a single atom. You see this as an ocean or a sea of electrons, and this really explains the conductivity of metals. Because the electrons are already flowing through, if you have another electron that's going to come on in, it's very easy for it to just move on through, because everything else is already moving on through, and your electron's going to come out the other side, which is why we use wires made out of metals such as copper to really flow electricity. All right, electron configurations for ions. I want you to get this as, somewhere in your head has to be. This is another thing you might just have to memorize, just like groups or periods. Don't make the mistakes here. If you have a cation, which is a positive ion, you have to remove electrons. The reason for this is electrons are negative. So subtracting or removing this negative gives you a positive charge. So we take our charges, our protons minus our electrons, and we'll use lithium here as an example. So if lithium has 3 protons, and if the charge is 0, well, our electrons would just be 3 minus 3. It'll be 3 electrons. However, if our charge is positive, our protons are still 3, but now 3 minus our electrons would be 2. So lithium plus has 2 electrons. The opposite is true for an anion, or a negative charge. So a negative ion has to gain electrons. Because electrons are negative, you're adding a negative to make the charge more negative. So if our charge is -1, well, then it would just be not 4, because lithium always has 3 protons. 3 minus 4. So now there'll be 4 electrons to get to a charge of -1. So you have to just memorize this. You have to be able to comprehend this, that if you have a cation, a positive charge, you're removing the electrons and you're taking them away. An anion with a negative ion, a negative charge, you are gaining electrons. You're adding them in. So here's lithium with 3 electrons. Here's lithium plus with 2 electrons, and here would be lithium minus with 4 electrons. So all you are doing here is just taking, adding, or subtracting however many extra electrons there are. Okay, so here's lithium, 3 electrons. Lithium plus, we got rid of that one. Lithium minus, when there's 4 electrons, we just added one in. Okay, so just as another example, if we take oxygen, oxygen has atomic number of 8. So oxygen would have 8 electrons. Oxygen 2 minus, negative charge, negative, gains electrons, would equal 10 electrons. Oxygen 2 plus. So a cation, a positively charged ion, subtracts those electrons. You would have 6 electrons. All right. Okay. The exception to this is these transition metal ions, because we are going to be using these to make our ionic bonds come January. When you have a transition metal, so remember, here are the transition metals. We're talking groups 3 through 12, only for these elements. And as we're going to see, it's due to the D block, due to those D block electrons, only these metals. When you are taking an ion and you have something that looks like this for zinc, because of the closeness of energy of the 4s and the 3d, you remove the 4s or any s before you remove any d electrons. So here is zinc, 4s2, 3d10. I'm only focusing here on these electrons here. If you are going to make zinc 2 plus, remember, positive charge removes electrons. You remove the electrons from the s orbital first. This is okay. This is the correct electron configuration for zinc with a positive 2 charge. It's kind of a first in, first out. It's like you got on the bus, you get off the bus first. Only for this exception between the s and the d orbitals, just because of the closeness of their energy. It gets complicated, but this is one of those exceptions you need to know. Okay? And the next example that I have on the screen is an example with iron. Here is iron, 4s2, 3d6. There are 6 electrons here, 2 electrons here, to make Fe2 plus, where you are removing 2 electrons. They come first from the 4s, so you would have 0 electrons here and 6 here. To remove 3 plus, to remove a third electron, now we're going to get rid of this electron, and we have 3d5. Transition metals will only form cations. I will not ask you for anions. Anything that I ask you for an anion is not going to come from a transition metal. Just want to make that up front as clear as possible. When we are dealing with the transition metals, it is only going to be cations, only removing electrons. I will not give you an example of a transition metal where you have a negative charge. Okay, so we are now talking on section 4, where I talk about the structure of the periodic table in relationship to electron configurations. So in class, I did this, and I know some of you are absent, and I totally get that. But we're going to just do a brief overview. When you start adding in electrons and you start adding electrons, doing our electron configurations, we start to see a trend. So what I've done is just adding in the last orbital filled in and how many electrons there are in there. And pretty soon we start to see this pattern where we start to see that our electron configurations are built around the periodic table, where there are 6 electrons that can fit into p orbital, and wouldn't you know it, 1, 2, 3, 4, 5, 6. So we start to see this pattern form, that there are 6 electrons from group 13 to 18 in this period. And what we start to see when we start doing all of this is something that looks like this, where we have our 1s orbitals filled out by groups 1 and 2. Helium is an exception over here. Helium is usually put here just because of its similarities to other noble gases. However, once we start getting to lithium, there's our 2s. I'm going to put the periods up here at the side just to show you as well that here we're in period 2. Lithium starts with the 2s. Period 3, 3s. Period 4, 4s. Period 5, 5s. The d orbitals, we start at d. 3d is going to be in period 4. The F, if you really wanted to, just perhaps I might ask an extra credit question on it. Here is the F up here. So it would go 6F, 6S, then the 4F, and then the 5D, and then the 6P, if you are just curious, in case I answer a question about that. What we can take from this is that we can pretty easily get electron configurations just by looking at our periodic table. The example I used in class here is iodine, where we start to see how to get an electron configuration is just really going through this. Well, we start off with a 1s, and you just fill it up as much as you can. 1s, 2, there's always going to be 2 in an s orbital. 2s2, always going to be 2 in an s orbital. Here's our 2p, and it even says on this map here, or this table, that there's going to be 6 in here, there's going to be 10 in here, there's going to be 14 in there. 2p6. We move on to the next orbital, because these are still full. 3s2. Move on to the next orbital. 3p6. Keep moving on. I'm going to run out of room here, aren't I? See if I can fit it in. 3d10. 4p6. 5s2. I'm just going to... Yeah, I ran out of room. 5s2. I'm going to keep going down here. 5d10. And then finally, 5p. And here we are, number 5. So if we go 1, 2, 3, 4, 5, we would be at 5p5. So we can use this to get any electron configuration that we want. And I'm probably going to ask you to do this. I'm not going to give you the charts like I did on the other tests. I'm not going to give you the order. I would give you something like this and say, give me the electron configuration of iodine or anything on here. And I'll make you write all this out. This is very long. I'm very aware of that. So this is why we have our noble gas electron configurations. This is our 6th part. So to do this, and I'm just going to erase all of this here, and I'm going to go back to our periodic table here, erase all of this. This actually, website, why I love it so much, it has the same things that we've been going through color-coded. And you can actually see they put helium over here. Okay. The reason, and I think this is just a good detour, now that I'm really thinking about it, the really good reason that that helium is usually over here is because helium is a noble gas. Here's our noble gases. As a general rule, elements that are in the same group have similar properties. The videos that I showed in class, all of the the alkali metals here, they are all super reactive, will explode with water. All the noble gases over here, and helium, they are inert. They do not react with any other elements. They have similar properties. There's a reason why we use these for coins. Why we use copper, silver, and gold for coins historically. Why gold is so valuable and silver so valuable. That's not by chance. Well, them being in the same group, not by chance. So elements in the same group have some similar properties. So, with this being said, to get the noble gas configuration, I had that whole big thing for iodine, that super long electron configuration. What we can do to make this really easy, I'm going to take aluminum here, just as an example. The best way to do this quickly, first, here's our element. You want to find the noble gas that is in the period above the element you are looking for. Here is aluminum. I'm going to go up a period. We're in period 3. We're going to go to period 2. Up an element and find the noble gas, which remember is up here. And I'm gonna put helium over here. Helium is there. Don't forget helium is there. Helium is there. So we're gonna go up one period all the way to the right, and we're gonna find neon. And what we can do here is we can say for aluminum's noble gas electron configuration, how we do this. This is the noble gas electron configuration, and it is a shortcut which makes our lives incredibly easy. You take brackets and you write that noble gas inside of it. What you've done is cut out all the junk. You've cut out the 1s, you've cut out the 2s, you cut out the 2p. And all you are left with is here is our 3s, and here is our 3p. So we have 3s, 1, 2, 3s, 2, and then we have our 3p, and there's just a 1 electron in there. 3p, 1. And this gets rid of a lot of the junk, a lot of the redundancy, 1s2, 2s2, all of that stuff that you have to do many, many times. And this is really great when you get to an element like iodine. So this is the example that I did in class 2, and I want to do this here. So, for iodine, I'm going to put this, let's see, I'm going to put this right here, bottom left corner. Here's iodine. We're going to go up a period and find the noble gas, which is krypton. So it's always the noble gas. You're always finding the noble gas in group 18 here. Okay? So here we take krypton, Kr, and put it in our parentheses. Now, well, this is period 5, so guess what this is going to be? 5s. Here's our 3d, and you're going to get this on a quiz, so you should have access to this to help you. That this is our 5s, here's our 4d, here's the 5p. I do want to give this to you. So here's our 4d, and here's our 5p. Well, we have 5s, 1, 2, 5s, 2. This 4d is complete. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 4d, 10. And then in our 5p, 1, 2, 3, 4, 5. 5p, 5. This is the noble gas electron configuration for iodine. And as you can see, I can fit it on the screen without running out of room. Much, much shorter. Or as I said on our paper, much better. If you get that reference, you might be a 90s kid. Alright? The final thing that I want to end for our scholars discussion is valence electrons. And you might have seen valence electrons in the past. Some students have said they might have learned about it in biology. You've probably seen something like this. Valence electrons on the outermost shell of the atom, and they're the ones that are able to interact. And this is why they're important, because this is true that they are able to interact with other atoms to form chemical bonds. So that is why they are super, super important. However, we've gotten away from this model. This is our two-dimensional model with the rings, and it's not as clear. We've gotten from that to all these orbitals, right? We've gotten to this 3D model that looks something like this. Here's our three-dimensional model of an orbital. This is a 2p orbital. So something that looks like that, a lot different than something that looks like this. So it is still true that they are still the outermost shell, the outermost ring, but those rings now are these numbers, these in front of our orbital. So 1s, 2s, 3s, that 1, 2, and the 3. So what that means is that we only care about the outermost, which is the period. It matches the period. It's the best way that I want to go for it. So if we take aluminum here, aluminum is in period 3, right here. Here's aluminum, period 3. Which means that we only care about electrons where 3 is our number, the number of the orbital. Those are the valence electrons. So aluminum would have 1, 2, 3. 3 valence electrons. Nice, easy, simple. However, if we go down to iodine here, here's our iodine here. Iodine is in period 5. So period 5 means 5s2. We count those as 2. 4d10, we do not count them for our valence electrons. If we want to go back to that shell theory, they would be in the 4th ring, not the 5th ring. But I wanted to get through electron configurations in the 3-dimensional model. It's more accurate, so that's why this model does not work as well. 5p7 does count. We have 2 plus 5, and we have 7 valence electrons. You can expect me to ask. I will give you something like this. 5s2. Why don't we count the d10? Why don't we count the 4? I'm going to ask that. Just because once I give you the easy way to calculate valence electrons, I still want you to know the background behind it. So you're still going to have to do it. But what we've basically done with the noble gas electron configuration 2 is said that everything that's not here, everything that is krypton, which is all of these electrons here, they're core electrons. They're in the middle. They're attracted to the nucleus. It's the valence electrons, that 5s and that 5p, that are the furthest away from the nucleus, and they're able to chemically bond. And we're going to spend a lot of time on chemical bonds, so we're going to need to know our valence electrons pretty well. Luckily, there's a few ways to easily get the amount of valence electrons that an element has. I'm going to clear this. First and foremost, we are not dealing with valence electrons for any transition metals. We're definitely not using these. The easy way to do this, I'm going to get off of I'm going to go to the Properties tab. Easiest way to do this is to look at the group. So again, not using this, not using this. 1 valence electron. I'm using VE to represent valence electron. Group 2. 2 valence electrons. Group 13. 3, 4, 5, 6, 7, 8. So once you get over to group 13, you just get rid of the 1. Ooh, goodbye 1. That's how many valence electrons there are. Very easy. Fluorine, 7. Chlorine, 7. Bromine, 7 valence electrons. Iodine, 7 valence electrons. Very easy. I will still ask you why we don't count these D. Why don't we count the D block? Why don't we count these electrons here? Well, because they're in a lower energy level. You could say they're in a lower ring. They don't count. They don't bond. That's the easy way to get valence electrons. And as I've said before, this class builds upon itself. So we went from electron configurations to the noble gas electron configurations to valence electrons. It's that flow. Me telling you the secret, or I don't want to say secret, but me telling you the easy way to calculate the valence electrons, that's just kind of the end goal. The flow of this class is the electron configuration, which gives us noble gas electron configuration, which leads us to valence electrons, and that's going to lead us to bonding. That's the flow of this class. It builds upon itself. We've been learning about the periodic table. We're going to continue to learn about the periodic table some more. But this is the biggest takeaway probably from this whole chapter that we're going to continue to use in the next few chapters. So that is all for Scholars Chemistry. There is one final thing that I want to talk about with the Honors Chemistry, and we're going to see this when we talk about periodic trends, and it's something that is important. So I do want to just go over that now. So the final thing for honors chemistry is knowing these exceptions and knowing why they are exceptions, because that why, we're going to see it when we start looking at exceptions to periodic trends. So you're going to have to get used to this. Here are two of the exceptions to electron configurations, chromium and copper. All right, if we go back to our periodic table, and we go back to our electrons, we would expect here, if we look at, I'm going to actually just go into chromium here, just to show you here that there is 1 in the 4s and 5 in the 3d. Right, so here's our 4s, and here's our 3d. So you would expect 4s1, 4s2, 3d1, 3d2, 3d1, 3d2, 3d3, 3d4. You would expect chromium to be 3d4. But instead, it is 4s1, and I'm going to use the noble gas electron configuration. This is what I kind of wanted to go through when I put this on our practice, but that's okay. 4s2, 3d4. This is what you would expect chromium to be, but in reality, it is equal to AR 4s1, 3d5. Looks something like this. Copper is very similar, but instead of 3d5, it's 3d10. So copper is equal to AR 4s1, 3d10. That's the second exception. This also holds true for these elements that I'm circling now. These are the only exceptions I would expect you to know. I will not give you anything else. You have to know these 4 specific elements. Tungsten actually gets really wacky, where it actually goes back to the D4. Gold continues the trend. It's weird. Like this one, Ronthogenium. I only want you to know these 4 elements. That's all I'm going to ask of you. I won't expect you to do gold. I won't expect you to do tungsten to know that. But molybdenum here follows this rule. Same with silver. Those are the only 4 elements I would expect you to identify as having a weird or messed up electron configuration. There's actually a whole bunch of them, especially when you get onto this F block here. I mean, this one starts with the D. We're not getting there, okay? So, the reason for this, I want to go back just to our slideshow here, is having a half-filled d orbital, or any p, d, something like that, where there are suborbitals. So there's 5 here. Having a half-filled or a fully filled orbital gives a form of stability. It is a little bit just extra stable, electronically, energetically stable to do that. The reasoning is not what I would expect you to know. I would just expect you to know the outcome from this is that in this instance, a D5, so S1 D5, which is S1 D5, is more stable than S2 D4, and S1 D10 is more stable than S2. That's a 2. 2. That's a 2. D, that should be a 9. Just please know that. Because we have extra stability here. Because when we get to periodic trends, you're going to see several times that there are those little weird exceptions, and most of the time it is due to a full orbital being filled. Okay? So we'll put a pause just, because we're going to see that later, but I want you to know these exceptions. On a quiz, I am much more inclined to be very explicit about there being an exception, such as I would ask you, why is copper, what is the electron configuration of copper, and why is it an exception? On a test, I'm going to give it to you and hope that you can identify it. Okay? So that is all for this video. I know this is a long video, but I hope that this is thorough with its explanation, talking about all the various different types of configurations and the structure of the periodic table, recapping groups and periods, the types of groups and periods, because, we use noble gas electron configurations because they're based on the noble gases. This is really just the setup for bonding. The periodic trends is just more information that I think is important because it talks about important skills, and it's a lot of reasoning, which is an important skill to have. So I hope you enjoyed. I guess where I do an outro, smash that like button, hit that bell, all that fun stuff. All right, take care.